Okay, alcohols. Um, let's just begin. So this is going to be obviously our IL chemistry. I'm studying this from chemguide, so it should have mostly everything we need plus more. And everything is going to be taught in extreme detail. So there's going to be a lot of repetitiveness. And this is going to be hopefully a long video. Um, so yeah, here we go. So introducing alcohols is our first topic. Just basically, to know what these things are. What we're learning are just what they are, what's the difference in primary, secondary, tertiary. It's going to be similar to haloalkanes. I'm going to be taking a lot of reference from there, so yeah. It looks similar in some detail as their physical properties such as bonding properties. Okay, so we're going to be looking at two things inside them. Chemically, we're going to be looking at their physical properties and such as solubility and boiling points. Then the detailed reactions are on later pages. So what are alcohols? Um, mm, okay, so alcohols, compounds in which one or more hydrogen atoms in alkane have been replaced with an OH group. So we have an alkane. So we have like a alkane like that, and there's hydrogens everywhere, and one of those hydrogens or more is replaced with an OH group. And we'll only be looking at ones which have only one OH group, similar to haloalkanes. So as you can see, ethanol propan-2-ol, 2-methylpropan-2-ol. This is really the same structure as we did the thingy, haloalkanes. So we're given over here that we have OH when it's bonded to alkyl group, which is bonded to only one, bond to alkyl group bonded to two, and bond to alkyl group which is bonded to, well, this is also bonded to only one. Alright. So here, looking at primary, we don't really need to know because we already know most of this. Okay, this is stuff where it gets kind of interesting. So we are given the boiling points. This is going to be our first physical property that we're looking at, and we're seeing the boiling points of simple primary alcohols with up to 4 carbon atoms. So what type of alcohol it is constant here. So that's going to be your control, but up to 4. So the size of the alcohol increasing, that's going to be your, so the size, or the MR, is going to be your independent variable, and the boiling point is going to be your dependent variable for these. Okay, so as you can see, they're compared with the equivalent alkane, methane to butane with the same number of carbon atoms. So we're given alkanes and we're given alcohols. Simply put, alkanes are just the same thing as alcohols, except one of those H's is replaced with an OH. Okay, so overall we can see that as the number of carbon atoms increases, the boiling points increase, but alcohols mostly have a way higher boiling point than alkanes. However, increasing the number of carbon atoms doesn't really increase the it does not really help the alcohols. Okay, but it does really help the alkanes. Okay, so look at that increase from there to like about there. It's a very big increase compared to here, which is like what? That's nothing, right? And we're having the same number of carbon atoms. So notice that the boiling point is always much higher, and the boiling points of the alcohols increase as the number increases. The patterns reflect the patterns in intermolecular attractions. So yes, this assumes that you have knowledge from the previous topic, which is going to be your intermolecular forces. We're going to be talking about your hydrogen bonds. This time we're going to be talking about hydrogen bonds. We didn't talk about hydrogen bonds last time when we were doing haloalkanes, mainly because there was no OH groups. So yeah, this time we have OH groups, so we can talk about haloalkanes. So the first one we're going to be talking about is going to be related. It's going to be your hydrogen bonding. It's going to be your first halo. It's going to be your first indication to the pattern of the boiling points. So we're going to be looking at the patterns of the hydrogen bonds, which will reflect the patterns of the actual boiling points changing. So hydrogen bonds, what are they? They're usually occurring between molecules where you have hydrogen atom attached to one of the very electronegative elements, which is fluorine, oxygen, or nitrogen. So hydrogen atom bonded to these. In this case of alcohols, hydrogen bonds are set up between the slightly positive hydrogens and the lone pairs and the oxygens in other molecules. So if we have two alkanes here, right, or two alcohols rather, we have one alcohol here, and we have one alcohol here, denoted by you have the R, which is the alkane going this way, R, which is the alkane going this way, and we're seeing the O having sorry about that. We could do this by doing it like this. Okay, yeah. So we can see that we have one lone pair and another lone pair here. This lone pair going this way and this lone pair going this way. Another lone pair going the same, pretty much the same way. And as you can see, the lone pairs are what? Lone pairs are going to be your negative, 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 and negative, right? And your hydrogen is going to be positive. Because as you know, when you have an H2O, this is going to be your positive, partially positive, partially negative, and these are going to be your partially positive, right? So that's the same thing here. This area is going to be your partially negative, this area is going to be your partially positive, partially negative, partially positive, okay? And the partially negative is going to be bonding with the partially positive here. And that's resulting in some pretty interesting stuff that results in a bond called a hydrogen bond between one hydrogen and one oxygen, okay? And one lone pair of the oxygen, not the other. So you could have another hydrogen from a different molecule that's bonding with this through a hydrogen bond. And that is what this blue line is. It's denoting that there is actually another hydrogen bond there, okay? So, and always these are going to be 180. So when you have your O, when you have your H, from the O, you have your other H, the hydrogen bond is always going to be 180, like this, okay? So you could have an O like this, imagine there's an H, but always it's going to be 180. Okay. Hydrogen atoms are slightly positive because the bonding between the electrons are pulled away because the oxygen atoms are electronegative. If you want to be fussy, the diagram is slightly misleading. That it suggests that all lone pairs on the oxygen are forming hydrogen bonds. Oops, am I wrong? In alcohol, that can't happen. I see. So in alcohol, let's actually switch highlighter colors to about like yellow. I prefer that. So in alcohol, you cannot form all lone pairs do not form hydrogen bonds, okay? That is because if you take the alcohol as a whole, there are only half as many slightly positive hydrogen atoms as there are lone pairs. At any one time, half of the lone pair. So what they mean by that is when you have H2O. Wait, what does that mean actually? There are only half as many slightly positive hydrogen atoms as there are lone pairs. At any one time, half of the lone pairs in total liquid alcohol won't have hydrogen bonds from them because there aren't enough slightly positive hydrogens to go around. So you need to know that there's not enough slightly positive hydrogens for it to happen. However, I thought since there are two lone pairs, oh, whoops, that's not H2O. My fault, guys. Whoops. We're talking about OH, not H2O. Two lone pairs, only one hydrogen. Okay, my bad. We're learning. Okay. So, yeah, OH, but then you have two lone pairs. So you're going to have two negative zones and only one positive zone. So, in the whole alcohol, half of you, there's going to be only, this will not be able to find the other H, because if you're only doing hydrogen bonding, that means OHs are only making hydrogen bonds with other OHs. That means there's always going to be that one extra thing that's not bonded to anything for all of them. So yeah, that is actually kind of interesting. In alkanes, the only intermolecular forces are van der Waals and dispersion are van der Waals dispersion forces. Yeah, as you said, there was no hydrogen bonds, because hydrogen bonds require an OH, and also there was no permanent because it was not a polar substance. Am I correct in that sense? I forgot. Yeah, because it was non-polar. I'm pretty sure that's what it was. If I'm wrong, then it doesn't really matter because we're not talking about it. Hydrogen bonds are much stronger, so therefore it takes more energy to separate alcohols than it does separate the alkane molecules. That's the main reason why boiling points are higher. So the boiling points are higher because literally just hydrogen bonds are stronger. That's it. And require to take more energy to separate alcohol molecules than alkane. Now, the effect of the van der Waals forces, so this is going to be your second force that's involved, other than hydrogen bonding, and it's going to be affecting the boiling points on the alcohols. We're going to be talking about how it affects the boiling points on alcohols, as we did for the hydrogen bonds. Now, hydrogen bonding isn't the only intermolecular force in alcohols. There's also van der Waals and dipole-dipole interactions. Okay, yeah. Here there are dipole-dipole interactions because there is electronegative. I'm pretty sure there's a polar side, there's a non-polar side. So you also have your van der Waals and you have your dipole-dipole interactions, and the hydrogen bonding and the dipole-dipole interactions will be much the same for all alcohols, but the dispersion forces will increase as the alcohols get bigger. So this and this will usually stay the same, but as the for all alcohols, but as the alcohol gets bigger, the dispersion forces also get bigger. So if you had your hydrogen bonding, your dipole, and your van der Waals, and your size, or your MR, as MR increases, this also increases, but these will usually just stay around the same. And these attractions get stronger as the molecules get longer and have more electrons. That increases the size of the temporary dipoles. Ashi! And this is why the boiling points increase as the number of carbons in the chain increases. As it takes more energy to overcome the dispersion forces, the boiling point rises. Same thing always. And we're comparing the alkanes and alcohols, we'll see that if there wasn't any hydrogen bonding or dipole-dipole interactions, then the boiling point of the alcohol would be higher. But let me repeat. Hydrogen bondings and dipole-dipole interactions didn't exist, then the boiling point of the alcohol would be higher than the corresponding alcohol with the same number of carbon atoms. Even if there wasn't any hydrogen bonding. So if you had ethane and ethanol, ethanol is a longer molecule, and the oxygen brings with it an extra 8 electrons. Both of these will increase the size of the van der Waals. So if you were really doing a fair comparison to show the effect of hydrogen bonding, it would be better to compare ethanol with propane rather than ethane, because then you would be having around the same amount of electrons. The length would be would then be much the same, and the number of electrons is exactly the same. So when you start with ethanol and ethane, right? Over here, ethanol, we have C2. No, sorry. Well, yeah, we have C2, H4OH. 1, 2, 3, 4, 5, 6, 7. 2 1 plus 2, right? So that'll be 2 times 2 equals 4 plus 2 is 6. So C2H5, but then it'll be minus one of those C2H4, which I believe that's what it is. But yeah, so that, and you're comparing that with C2H5, which is this 1, 2, 3, 4, 5, 6. Sorry, dude. 2n plus 2. If you had 2 times 2 plus 2, that's 6. So that would be C2H5OH. That's why this one looked better. And that would be C2H6. This is C2H6, this is C2H5OH. And yeah, over here you also, so it's pretty much a longer molecule in terms of size, and also has more electrons than this. And so even from the starting standpoint, this already has like a way bigger head start. Now you talk about solubility. Okay, it's been a little while, but we're back. Is everything okay? Yeah, everything looks okay. So now talking about the solubility of alcohols in water. So our solvent is going to be water, and so that's going to be our control variable. Alcohol is also control variable. Independent variable is going to be our dependent variable is going to be our solubility. What's going to be changing is going to be probably the sizes of the alcohols. See, one thing to note, I think is kind of interesting, is when we had haloalkanes, right? There were some interesting things. First of all, size would kind of have to do with MR, right? And MR would have to do whether if you're using iodo or chloro or, you know, the other one. I forgot the names, but those are what would really cause the difference, like in size at least. And these would have their own, you know, chemical properties. And same thing with, you know, your, you know, primary, secondary, that kind of stuff. So there would be your type. There would be what halogen are you actually using, right? And then there's also the size in terms of just like branching, right? So over here, you know, you say small alcohols as in small number of branches, but that would actually be the same thing as saying like using chloro, right? But when you have a longer one, that would be the same thing as saying using like iodo. Okay, so yeah, that's maybe a cool little connection. Then over here it says small alcohols are completely soluble in water. They're completely soluble. Okay, and we're talking about small alcohols. Whatever proportions you mix them in, you get a single solution. Okay, so they're super soluble, completely soluble in water. We're talking about your small alcohols. Okay. However, solubility will fall as the length of the hydrocarbon chain of the alcohol increases. Okay, as you get to 4 carbons and beyond, the solubility is noticeable, and you may well end up with 2 layers in your test tube. Shit, tragic, man. So what's going on here? The solubility of small alcohols in water. Consider ethanol as a type of small alcohol. In both pure water and pure ethanol, the main intermolecular attractions are hydrogen bonds. Now, in order to mix the two, you would have to break the hydrogen bonds between the water molecules and the hydrogen bonds between the ethanol molecules, which requires energy to do both. However, when the molecules are mixed, new hydrogen bonds are made between water molecules and ethanol molecules. As a result, the energy released when these new H bonds are formed more or less compensates for that needed to break the original ones. Meaning, when we have the base, like when we have like this is the original state, and the activation energy to get to break them, the amount of energy lost will actually bring them down to more or less the same plane as the previous one. The energy level or energy difference between the products and the reactants in the products are not that different. That's why this reaction it doesn't require any energy input. They are soluble naturally. Okay. So again, we have this and we have the products, and they are pretty much on the same energy level. Maybe one is a bit higher. And when you input energy, you have to reach this certain amount. That's going to be activation energy. But then after you reach the activation energy, more or less, since you're making the same types of bonds again, you're gonna reach pretty much the same energy. Like you're gonna release pretty much the same energy as the amount of energy you raised. So this is one arrow. It's going up. That's gonna be the amount of energy absorbed to break the bonds, and this is the down arrow, the energy released when forming the bonds. So in addition, there's also an increase in disorder of the system, which is an increase in entropy. There's another factor deciding. That is another factor in deciding whether it happens or not. If you haven't we haven't come across entropy, we don't need to worry about it. I mention it because the energy released when the new bonds isn't quite enough to compensate for breaking the old ones, meaning that the mixing process is endothermic. If it weren't for the increase in entropy, the solution wouldn't have been formed. So it's actually like, it like naturally it would be like this much, and then entropy covers this last bit, which makes it a fully natural process where a solution can be formed. However, if it wasn't, then it would be endothermic and the reaction wouldn't happen. To understand this, you would need to have studied entropy and free energy. If you should know about this but not happy about the calculations involved, you might like to look at chapter 11. You might do that. Now, the lower solubility of alcohols. Imagine what happens when you have got, say, 5 carbon atoms in each alcohol molecule. So we have H2Os, we have carbon chains, and we have alcohols with 5 carbons in each alcohol molecule. And the hydrocarbon chains are forcing their way between water molecules, so breaking hydrogen bonds between those, which are breaking the hydrogen bonds between those molecules. So you got like hydrogen bonds like between this guy and this guy. Like there's a hydrogen bond like going this way. However, the moment this guy comes in between, then it breaks these hydrogen bonds, correct? And as a result, the OH end can form new hydrogen bonds with the molecules. So after it breaks the hydrogen bonds between these, it can actually form new hydrogen bonds like this, and also like this and like this. You can only form 2, but that's what I mean. Like, because as you move, it'll break and it'll form new hydrogen bonds with new water molecules. Now the OH end will form new ones, but the hydrocarbon tail doesn't form hydrogen bonds, of course. That means that quite a lot of the original hydrogen bonds being broken aren't replaced by the new ones. That means quite a lot of the original hydrogen bonds being broken aren't replaced by new ones. All you get in place of those original hydrogen bonds are van der Waals dispersion forces between water and the hydrocarbon tails. These attractions are much weaker. That means you don't get enough energy back to compensate for the hydrogen bonds being broken. Even allowing for the increase in disorder, the process becomes less feasible. So as the length of the alcohol increases, the situation just gets worse, and so the solubility falls. Okay. Sorry, I didn't really read this part, but this is the explanation for bigger alcohols, lower solubility, as in bigger alcohols, lower solubility, like that. So yeah. if you have a larger alcohol, then more hydrogen bonds will be broken in terms of like this, I'm guessing. So since there's going to be like a larger hydrogen bond here, breaking the hydrogen bonds, since there's going to be a larger alcohol here, breaking the hydrogen bonds between the water molecules, you're breaking them, but you're not really forming new hydrogen bonds, right? You're breaking them, you're breaking more hydrogen bonds than you're forming. So therefore, it's an endothermic process, which means that it'll become less feasible for for solubility to occur, correct? And Ned did mention that after you break the hydrogen bonds, the only thing you get back, or the only thing that's keeping them together, is the van der Waals dispersion forces. Now, what van der Waals dispersion forces are we talking about? We're talking about the dipole, like the instantaneous dipole that's formed between the nonpolar molecules. We have H2O and we have CHs everywhere, right? So the instantaneous dipole, or maybe perhaps the instantaneous dipole which happens over here and over here, or even perhaps from the C to the H when you have a C over here and H on the outside, that instantaneous dipole that happens over there, that's what's going to increase. No, sorry, that's going to occur the moment when you have an H2O that's right next to you, right? So there you have it. There you have like one dispersion force happening over there. So yeah, when you have larger, although when you have larger alcohols, you're going to get larger instantaneous dipoles, which means larger boiling points. You're going to get a lower solubility because, again, although these instantaneous dipole forces are increasing, you're having the bigger problem of actually breaking more hydrogen bonds between these and these. Then you're actually forming new, new van der Waals attractions between them. The energy formed by those is just not enough to compensate for the hydrogen bonds that you're breaking. And so as the length of the alcohol increases, the situation just gets worse and the solubility falls. Now, how alcohols are made. So there's two ways to make alcohols. We can make them from alkenes by reacting it with steam. We learned this in from paper 1. And we're making other alcohols from alkenes. Ethanol specifically from fermentation. I remember that as well. This was in GCSE. And that's going to be your only two, right? Hydration of ethene and your thingy. So that's good. It's nothing too tough. Actually, I think they said the word GCSE here. Did I read that correct? I don't know. So they're going to include a lot of practical knowledge here, perhaps. So yeah. So first of all, you're making it from alkenes. So that, remember that this is going to be your double bond, right? And since you're creating it from your double bond, then you're probably going to have something that looks like you're, breaking the double bond. So, hydration or something like that. So let's see. If you're making ethanol from ethene, right? So this is specifically ethanol from specifically ethene. You're going to be reacting ethene with H2O in the form of steam. And the catalyst that you use is phosphoric V acid, right? So again, you have your thing over here, you have your H2O, you have your catalyst, and you'll form this in the end. Now there's probably a mechanism going on here. Yep, there's a mechanism. We'll go to it, although I think we do know it. So over here we have your little thingies, your conditions. So only 5% of the ethene is converted into ethanol at each pass through the reactor. By removing the ethanol from the equilibrium mixture and recycling the ethene, it's possible to achieve overall 95% conversion. A flow scheme of the reaction looks like this. So you're going to have your first amount of ethene, you're given 1 given volume plus 6 given volumes of steam, which will react to form 300 with the conditions 300 Celsius, 670 atm atmospheric pressure, First word be acid catalyst, and you'll form gases which are cooled, and ethanols can turn to liquid, with the unreacted gases being recycled back, and the unreacted gases being your ethene, and your liquid being your ethanol. Simplification: when the gases are from the reactor are cooled, then the excess steam will condense, as well as ethanol. Ethanol will have to be separated by fractional distillation from the water. This is not the same thing as the other kind of distillation, I'm pretty sure. But perhaps I'm wrong. All the sources I've looked at gloss over this, so I don't have any details. I assume it's normal fractional distillation for a phenethanol water mixture. If you're really interested in the reasons for conditions used in this reaction, you'll find them in the equilibrium section of the site. I'm not. If you're interested in the mechanism, follow this to the catalysis section. Because these pages are somewhat illogically in different parts of the site, use the back. Okay. Oh, this is a good song. It is open. Before we go talk about it, let's see if I remember it. So you're gonna have your CH2. Well, that's not really the CH2 I'm talking about. You have your CHH. Forget my horrible thing. Right, you have your other CH. And it's gonna be your double bond. Okay. And you have your H2O coming in like this. And your H2O is gonna form it like, right? And it's gonna be kind of your electrophile kind of thing. And then what are we having? We're gonna have I don't remember quite well. Damn it. Okay, let's see. This assumes that you already know about electrophilic addition reactions of ethene and about the use of cardianos in organic chemistry reactions. If you're unhappy about either of these, I am okay at these. I am not very good at explaining electrophilic addition of ethene, but I do remember like something removing the ethene bond. So if you're like CH2, basically like the H gets removed, the double bond, no. No. This is gonna be your like negative, so it goes inside here, forming what appears to be like your you know, your H, single bond H, you have two H's here. This is gonna be like your plus, and you're gonna have the remaining O negative H. This is gonna be like a negative thing. This goes over here, and then you have OH, H, and then H, something like that. So all the steps in the mechanism are shown in one-way reactions because it makes the mechanism look less confusing. So you just need to remember that these are electrophilic additions, okay? Why? Because you have one electrophile, which is going to be your nucleus over here, sorry, the double bond over here, okay? And the OH is it electrophile? I don't remember what electrophile is. It's like electron donating. So your OH, your H2 is going to be electron donating, or something of that sort. Anyway, I just like to remember it as, you know, your double bond breaking, allowing the carbons to have one more H's on both sides. Okay. So all of the hydrogen atoms in the phosphoric V acid are fairly positively charged because they're attached to a very negative oxygen atom. One of these hydrogens is strongly attracted to the carbon-carbon double bond. The pi part of the bond breaks and the electrons in it move to form new bonds with the hydrogen atom. So we're having an arrow downwards, and okay, we are drawing the H2O bonded with the phosphate, which is kind of scary. So we're just talking about phosphoric acid. We're not even talking about water anymore. Huh. So this is not the way we did it. So, in this case, we're going to start off with your phosphate ion over here, okay? That's what your phosphate ion looks like. You got your P and your W, your double bond, and you're connected to three different O's, which are then three different OHs. Okay, you can think of it like that. You have one P, double O, connected with three OHs. Okay. Now these OHs obviously are going to be, polar, right? So when you have your positive and your negative, your H is going to hit your O like this. The H bond is going to hit your O like this. And there's going to be a CH2, double bond CH2. And that's going to go in between like this, resulting in. Or you could just do it like hitting the H directly, forming a CH3 single bond CH2 with a plus bond being on the CH2, okay? Plus charge on CH2, which then gets hit by an H2O, okay? Which has a double, which has like a negative part on it, and that will form. I see what's going on here. So you have your CH3 and your CH2 with the plus charge on it, and you're gonna well, this is actually neutral charge. This is not. This is negative, but it's more like it's neutral, because this entire thing is a neutral thing. Although this is partially negative, partially positive, that's the key word, partially. This is still overall a this is still overall a neutral thing. So after this hits this, or hits rather this this positive part, the electrons are given to form that bond. After that bond is formed, your negative is gone to this bond, which leaves this as a positive, which then is hit by another. Oh, I thought it would be hit by another H2O. Granted, this is what we did in halogen alkenes when binding with the amines, right? So, anyways, you have your CH3 CH everything, which is with the positive charge, and that's gonna be hit by another phosphate ion group with an O on it. Okay, and what's gonna happen is that the H is gonna go back into here, give the O its its lone pair, and then it's gonna form that H bond with the O, which is a negative charged double bond, negative charged lone pair. So on your H2O, you had it like this. This is overall a neutral thing. But then when you have your O, P, OH, OH, with your double bond on your H. Oh wait, this is not a phosphate group. This is a dihydrogen phosphate group. Is it the one that we removed the H from? I believe so. Yep, it is. So remember, it forms this as a product, okay, with this, and so comes in the catalyst with this, reacting the H back into this, forming the lone pair is gone from the H and it's gone back to being used to form the bond with the H. Lone pair is gone from the O, sorry, leaving O as neutral and forming the H bond, and so the phosphoric V acid has been regenerated. Now if I read it a little bit, it says that the easiest way of remembering the oxygen has a positive charge is if you're reacting a positive ion with a neutral molecule. That means that somewhere there must be a positive charge on the product somewhere. Right, so if you have a positive charge on the CH3CH2 and your neutral is your H2O, then the product will have a positive charge somewhere. And the only way the oxygen can be joined to three things at the same time if it carries an oxygen charge. Because OH is chill bonding to two things, but now O is chill bonding to three things, but now it's freaking out when it's bonding to more than two things. Now it's a positive charge. So a positive charge gives oxygen the same electronic structure as the nitrogen atom, which of course can form three. Yes, this is what I meant. It forms. This is a similarity to halogen alkenes, where we bonded with the nitrogen. It forms the same structure as a nitrogen atom, which can form three bonds. So in this case, a nitrogen atom would have been fine here. It would have been NH3, or sorry, NH2 with CH2. It would be three bonds. It would be chill. But no, it's a positive charge here. So then it binds with your dihydrogen phosphate ion. This is a bit of simplification. Concentrated phosphoric V acid particle contains some water. Into the water and the steam, it is most likely that some of the hydrogen ions in this last step will be removed by water molecules and possibly transferred to the dihydrogen ion like phosphoric acid. And last later step, hydrogen ions will be removed directly by dihydrogen phosphorylation as above. Don't be worried about this. Okay, cool. So going back, now if we're forming alcohols from alkenes, we did from ethene specifically. Whoops. We manufactured alcohols from alkenes specifically ethene from ethanol from ethene. Now we're doing other ones. So some, but not all, other alcohols can be made by similar reactions. Catalyst use and reactions conditions will vary. The only set of conditions you're going to need for UKLO purposes are those given above for manufacturing ethanol, so the same ones. The reason that there's a problem with alcohols is well illustrated by trying to form an alcohol with propane, CH3, CH2. So in principle, there are two different alcohols which might be formed. You have a propane 1-ol and your propane 2-ol, because why? If your HOH goes in there, first of all, this needs to open up. Okay, so this opens up, right? This becomes a single bond. The double bond could go either. Where does the double bond go? The double bond could either go to the left side or the right side. If it goes to the left side, to the CH, then it will form like this and OH on this side. If it goes to the right side, makes a CH3, then the OH will land on the left side. As a result, you'll have your propane 1-ol and propane 2-ol. And you might expect to get either propane 1-ol or propane 2-ol depending on which way the thing adds to the level. In practice, this is how you get propane 2-ol. If you add a molecule HX across a carbon-carbon double bond, the hydrogen nearly always gets attached to the carbon with the most hydrogens on it already. In this case, the CH2 rather than the CH. The reason for this is dealt with in detail. This, I'm guessing, is because of the primary carbocation stuff, because it has the most. I don't really care about this. I feel like I already know this. The effect of this is that there are bound to be some alcohols which make it it is impossible to make by reacting alkenes with steam, because the addition would be the wrong way around. Okay. So the effect of this is that, since there are bound to be some alcohols to be made, which you don't want, and those alcohols are impossible to be made when you react alkenes with steam, the reaction with addition is like sometimes not used. So, anyways, making ethanol with fermentation, this is the only applies to ethanol. You can't make any other alcohol this way. The process specifically starts from. There's a lot of text. Okay, is there any link here? Okay, dokie. So let's just read. It's gonna be really boring though. So you start with, your starting material can vary widely, but will normally be some kind of starch, plant material such as maize or corn, wheat, barley, potatoes. So it contains starch, or your carbohydrate. Now, starch is a complex carbohydrate, and other carbohydrates can be used, such as lab sucrose. Industrially, though, this wouldn't make sense, since it would be silly to refine sugar if all you were going to use it for was fermentation. There's no reason why you wouldn't start from the original sugar cane, though, right? So why would you, the sugar which is already manufactured, all that money spent into manufacturing that sugar itself when you could just be using the raw material. So yeah. Now the first step is to break the complex carbohydrate into simpler ones. For example, if you're starting with starch and grains like wheat and barley, the grain is heated with hot water to extract the starch and then warmed with malt. Malt is germinated barley, which is containing enzymes which break the starch into simpler carbohydrates such as maltose. So after you warm it with malt, then it breaks down the starch into simpler maltose carbohydrates, which is, I'm pretty sure, it's still a polysaccharide, or perhaps it's gonna be a disaccharide. I'm not quite sure. No, it's definitely a polysaccharide. So maltose has the same molecular formula as sucrose, but contains two glucose units joined together, whereas sucrose is one glucose and one fructose. Yeah, there you go. So it is it's just repeating units of maltose. One sec, let me just check. It is a disaccharide. Okay. Dude, I'm just gonna make some coffee. I'm really sleepy. I'll be back. Okay, whatever. So if you're starting, okay, so you have maltose, right? Maltose is gonna be disaccharide. It's gonna be, from 2 glucose units rather than 1 glucose and 1 fructose, which is what sucrose is, which is actually your original. Is your original? I don't even remember. Why are we talking about sucrose here? Oh yeah, talking about sucrose as in that's gonna be your lab sucrose, right? So that's gonna be your lab sucrose rather than your raw, sugarcane. So then yeast is added and this mixture is kept warm, 35, for perhaps several days until fermentation is completed. Is kept in the mixture to prevent oxidation of the ethanol. Produced ethanoic acid. So this is kind of cool. You want to keep air out so that you prevent oxidation. Right. So it's kept out to prevent oxidation of the ethanol produced ethanoic acid. So if it isn't, then the ethanol produced would be gone to ethanoic acid. It would be a carboxylic acid. Now ethanol and the enzymes in the yeast will convert the carbohydrates like maltose or sucrose into simpler ones like glucose and fructose, both this, and convert these in turn into ethanol and carbon dioxide. So again, we're seeing that it's first your maltose plus your water gone into this, which is going to be your glucose, and then the glucose is then turned into your alcohol plus your carbon dioxide. Okay. You can show these changes as simple chemical equations, but the biochemistry of these reactions is much more complicated than this suggests. Yeast is killed by ethanol concentrations in excess of about 15%, and that limits the purity of the ethanol that can be produced. The ethanol is separated from the mixture by fractional distillation to give 96% pure ethanol. For theoretical reasons, it's impossible to remove the last 4% of water by fractional distillation. If you're interested in this, you'll find it explored in here. So they're talking about specifically why you can't remove 4% of the pure ethanol that's formed from fractional distillation after you get the yeast, after the yeast is killed, and when you have your ethanol concentrations after that. If that makes sense. I know I didn't say that correctly, but like whatevs. So now your comparison between fermentation, your hydration of ethene, and fermentation of your 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 fermentation of your in this case it would be maltose, no, not maltose. What was maltose, no? Of your maltose into glucose into ethanol, right? So yeah. Fermentation is a batch process. Everything is put into a container to the left until fermentation is complete. That batch is cleared out and a new reaction is set up. This is inefficient. Whereas hydration of ethene is a continuous flow stream of reactions is passed continuously over a catalyst. This is the more efficient way. Rate of reaction is slow. The rate of reaction is fast. Reaction conditions uses gentler temperatures and atmospheric pressure. That means it's cheaper. It uses high temperatures, pressures, and a lot of energy inputs, so it's increased price. Use of resources, uses renewable plant-based materials, that's more better. It uses finite resources like crude oil, so that's a decrease in like renewability, sustainability of the reaction. So yeah, that's it. Now going on to dehydration of alcohols. These are based on like the more reactions of alcohols, so these are pretty important. And you're gonna be making some cool products here if I'm not wrong. So yeah, this page is a simple duplicate of a page in the section on alkenes. Looks at the dehydration of alcohols in the lab to make alkenes. For example, dehydrating ethanol to make ethane. So this is a way to make alkenes, but this falls under a reaction of ethanol or of an alcohol. So dehydration of alcohol using aluminium oxide as a catalyst, right? So I wonder if the halogenation page of this will also fall under, just be a copy paste of the other one. Uh, that would be kind of cool. So, dehydration of, so you, first of all, we're given some words here. We're using dehydration, so loss of water off your alcohol. Now, first of all, alcohol doesn't have water, so what are we talking about dehydration? Perhaps it means the removal of the OH group, right? OH group alongside one of the H's of the alkyl chain, using your aluminium oxide as a catalyst. Okay, so ethanol to give ethene, and as a result, you'll get ethene, which makes sense because when you got ethene, you put in your H and your H and your your H and your OH, one H to break the double bond, and your another OH to fill in the positive charge. In the same way you get ethene, you have to remove an H2O. So this is a simple way of making gaseous alkanes like ethene. If ethanol vapor is passed over a heated aluminium oxide powder, the ethanol is essentially cracked to give ethene and water vapor. So we learned about cracking, but we never learned about the specifics, so here we go. So first, to make a few test tubes of ethene, you can use this apparatus. So you want to put mineral wool soaked in ethanol and your aluminium oxide. So the vapor then goes over, reacts with aluminium oxide to form ethene as a gas, which goes into this test tube, goes in here, and of course it's not going to react with the water, and it's just going to go straight up and collects over there. Ethene, we haven't learned about the solubility of ethene in water. However, ethanol would react with water, as we know that it's quite soluble. Now, it wouldn't be too difficult to imagine scaling this up by boiling some ethanol in a flask and passing the vapor over aluminium oxide heated in a long tube. Correct. Now, dehydration of alcohols using an acid catalyst. Oh wait, we don't learn about anything else? That's it? Like that's all we're gonna talk about? Nicely. Okay. So now you have now you're having your the same thing, except now you're using a different catalyst. Now this can be either used with your sulfuric catalyst or your concentrated phosphoric catalyst. Sulfuric catalyst produces mesothelial results. Not only is it an acid, but it's also a strong oxidizing agent. Oxidizes some of the alcohol to produce carbon dioxide, and at the same time has reduced itself to sulfur dioxide. Both of these gases have to be removed from the alkene. It also reacts with alcohol to produce a mass of carbon. There are other side reactions as well, but these aren't required by the current UK RS level syllabus. Okay, so okay, we did not mention phosphoric acid. I knew of one chemistry teacher who put several students into hospital by getting it wrong. Okay, sorry. That was okay. That's interesting. Interesting. So here we go again. We have your two catalysts, right? But using sulfuric acid as a catalyst produces messy results. Now there are going to be several reasons why. First of all, it's an acid and a strong oxidizing agent. Now, I'm not very good at my redox. However, to know that it oxidizes some of the alcohol, right? Your alcohol has an H group, right? An OH group, and to oxidize that alcohol, okay, to carbon dioxide, right? So your OH turns into carbon dioxide, your CO2, by your sulfuric acid.